Hey, let's get it started. Stand on Earth 4.4 billion years ago, and nothing around you feels finished. The ground breaks, the sky glows, and the planet seems more like an accident than a home. Yet one crystal survived this world, a zircon dated to 4 billion years. It suggests that crust and liquid water may have appeared only 160 million years after Earth formed. So the mystery is not simply how life began, it is why a planet capable of building oceans kept transforming into places where almost nothing could survive. That tiny zircon changes the opening scene. Ancient Earth was not one endless ball of lava. It was a restless world that could form a skin, collect water, and tear itself apart again. Imagine standing on fresh black rock. The surface has cooled, but the cracks still breathe heat. Steam rolls across the horizon. An impact throws dust upward, while distant volcanoes release another curtain of gas. Nothing needs to hunt you. The landscape keeps changing the rules. Rock cooled, water gathered, heat and impacts broke the surface. Then it started again. The same cooling that created solid ground allowed water to remain. The active interior destroyed landscapes, then built new ones. Earth was assembling the pieces of a home while making the surface almost impossible to inhabit. For you, there is no breathable air above the ocean, no food, and no familiar shoreline. One part of the home exists, the rest is missing. Then microscopic life begins changing the air. It produces the gas every breath in your body depends on. That sounds like the moment Earth finally becomes safe. It is not. The mystery has an answer, and it is more unsettling than any prehistoric monster. Ancient Earth's deadliest eras begin when its basic life support systems change faster than living things can adapt. Air becomes poison. Water loses oxygen. Heat or ice erases habitats. And sometimes, life itself pulls the first lever. More than 2 billion years ago, the oceans belonged to microbes built for a world without breathable oxygen. Then, a new group learns to use sunlight for energy and releases oxygen as waste. At first, the gas reacts with material in the ocean and disappears almost as quickly as it forms. Think of wet iron left outside. It reacts with oxygen and turns to rust. Something similar happens across the ancient seas. The oceans absorb the waste until that chemical buffer can no longer keep up. Oxygen begins accumulating in the atmosphere. The major rise is dated to around 2 billion years ago. It may happen within only 1 to 10 million years. That sounds slow. For a planet, it is a door slamming shut. The organisms already living there have never needed protection from this reactive gas. Oxygen is not evil. Their bodies were simply not built for it. Evidence of the old atmosphere survives in ordinary-looking stones. Ancient river deposits contain rounded grains of pyrite and uranite. Water pushed them along the bottom, knocking away their sharp edges like pebbles in a stream. In today's oxygen-rich environment, those minerals would react and break down before surviving the journey. Their presence is a receipt from a world with radically different air. This is the pattern behind Earth's deadliest eras. The planet does not need to explode. One basic condition only needs to cross a limit. The same oxygen that threatens the old living world later powers larger and more active organisms. The poison becomes fuel. But as the chemistry of the sky shifts, part of the planet's warming blanket weakens. Temperatures fall. Ice spreads, reflects more sunlight, and makes further cooling easier. Oxygen has opened the door to complex life. Now the world producing it is sliding toward one of the longest freezes in planetary history. Once ice begins spreading, Earth enters a trap of its own making. Bright ice reflects sunlight into space. Less heat remains at the surface, allowing more ice to form, which reflects even more sunlight. Cooling starts feeding itself. Continents vanish beneath glaciers, and sea ice pushes toward regions that were once warm. Wind crosses a pale, nearly empty surface. The Sturtian freeze lasts roughly 58 million years. Human history would not register as a visible mark on that timeline. Mountains could rise and wear down while the same frozen era continued. But Earth is not a solid, lifeless snowball. Liquid water still moves beneath glaciers. Where ice presses against the seafloor, meltwater can carry oxygen into narrow pockets. Researchers describe them as oxygen oases, small zones where life may continue while much of the surrounding ocean remains hostile. Those subglacial pockets may have done the same for early life. The habitable planet contracted into scattered refuges. Eventually, ice retreats. Dark ocean and rock absorb sunlight instead of reflecting it. The process now works in reverse, and a white planet begins recovering color. But there is no old normal to return to. The next Earth is wet, green, and crowded. The air itself allows bodies to push beyond limits that once kept them small. Vast swamp forests cover parts of the continents. The ground is soaked and layered with fallen plants. Tall trunks crowd the light. Every step presses into wet debris, and the air smells of vegetation breaking down. Arthropods do not breathe with lungs like ours. Air moves through branching tubes that deliver oxygen directly into their bodies. That system limits their possible size, but oxygen-rich air can loosen part of the limit. This is where Arthropleura appears. Young specimens show 44 pairs of legs and eyes held on short stalks. Imagine it crossing the forest floor. Its legs move in organized waves beneath the body, while the raised eyes scan above the mud. The air changes the forest as well. Experiments show that natural fire becomes sharply suppressed when oxygen falls below about 18.5%. Above that threshold, flames spread more easily when other conditions are right. It works like opening an air vent beneath a fire. The fuel was already there. More oxygen helps the flame move. The forests create a dangerous combination. Thick vegetation stores burnable material, while oxygen makes fire harder to contain. A swamp can be dripping wet in one region and burning fiercely in another. Oxygen is both opportunity and risk. It supports larger, more active bodies, but also turns landscapes into fuel. The ingredient expanding life expands the ways life can be destroyed. Then, Earth crosses another limit. This time, the air, oceans, and forests begin failing together. The end of the Permian does not arrive as one dramatic explosion. There is no single morning when every ecosystem disappears. The planet changes through a chain of pressures, each one making the next harder to survive. Enormous eruptions in the region now called Siberia release gases and particles into the atmosphere. The danger is not a wall of lava chasing animals around the world. It is a change in life's background conditions. Seasons grow hotter, dry periods last longer, rain carries new chemicals into rivers and seas. The main pulse of marine extinction may unfold in only 61,000 years, with an uncertainty of about 48,000. Even the wider estimate is frighteningly brief for a planetary collapse. A forest can look permanent while already being doomed on the geological clock. The eruptions leave evidence far from Siberia. In Arctic rocks, a nickel isotope signal drops as low as minus 1.09 parts per thousand. Researchers connect it to nickel-rich material released by the eruptions and transported through the atmosphere. Fine particles cross the planet and settle where no lava ever flows. The eruption is the source. The atmosphere becomes the delivery system. Meanwhile, warming attacks the oceans. Warm water holds less dissolved oxygen than cold water, much like a warm carbonated drink loses its fizz faster after opening. Marine animals need oxygen, but the water becomes worse at carrying it. Their bodies demand more energy, while the ocean supplies less of what they need. Food webs lose their lower levels. Larger animals receive no warning. They simply find less food. Scientists examined roughly 800 fossil pollen grains from Tibet and found a response associated with stronger UVB radiation. The plants appear to produce more protective compounds, the biological equivalent of sunscreen. But sunscreen means something is already hitting the skin. Pollen carries the next generation. Damage it, and a forest can remain standing while its future disappears. The trunks remain, the branches still cast shadows, but fewer healthy replacements are coming. This is why the great dying belongs at the center of the story. Heat stresses animals. Ocean oxygen declines. Atmospheric material travels enormous distances. Ultraviolet exposure pressures plants. Each failure strengthens the others. Adaptation needs generations and survivors. When conditions move too far too quickly, even successful forms of life run out of options. The world that follows is not a clean restart. Survivors inherit damaged ecosystems and empty roles. Life rebuilds complexity, but the old arrangement never returns. And later, Earth creates another hothouse with a quieter horror. The next hothouse arrives in a world that is already warm. Carbon enters the atmosphere, temperatures climb, and familiar climate zones move toward the poles. The surface of the Arctic Ocean rises from around 18 degrees Celsius to more than 23. Imagine traveling north and finding water warm enough for a summer swim where you expect a frozen horizon. The map still says Arctic. Standing beside it tells you the planet has changed. Heat does not remain in the air. Carbon dioxide enters seawater and shifts its chemistry. Creatures building shells must work under conditions that make construction harder. Warm water also carries less oxygen, repeating part of the end Permian pressure. But the clearest change on land is shrinkage. An early horse lineage becomes at least 30% smaller during the first 130,000 years of the event. It is already small, and generations of it become smaller still. Smaller bodies release heat more quickly because they have more surface area compared with the tissue inside. A smaller body may also need less food when heat and changing rainfall make plants less reliable. No individual horse decides to shrink. Each generation contains differences. Animals whose bodies work better under the new conditions leave more descendants. Over time, the average changes. The climate is not sculpting one animal, it is filtering a population. That is a quieter kind of horror. Life remains present, but the world forces it into different shapes. Survival can hide the scale of the crisis, while habitats, bodies, and food sources are rewritten. Long after the hothouse fades, humans enter a world moving in the opposite direction. The ocean pulls away from the continents. Ice expands. The atmosphere fills with dust. This time, someone is there to remember the cold. By the last great glacial maximum, humans are already part of the landscape. They follow animals, search for fuel, and cross ground that was once underwater. The world is colder, but also far dustier. Greenland ice from this period contains roughly 100 times more dust. Each layer captures particles that crossed enormous distances before falling with the snow. As ice sheets grow on land, coastlines move outward. During the final approach to the lowest sea level, the ocean falls about 40 meters in less than 2,000 years. A harbor does not become shallower, it disappears, and the coast may move beyond the horizon. Exposed surfaces connect regions, widen plains, and provide fresh material for wind to lift. Cold air holds less moisture. Vegetation thins, leaving soil unprotected. This is not a clean, white Ice Age world. It is gray, brown, dry, and abrasive. Imagine waking beside a small fire. Dust has settled on the hides covering your shelter. It sits between your teeth and dulls the sky. The animals you depend on have moved, and the shoreline is farther away than it was for your grandparents. Here, planetary change becomes personal. The same systems that reshaped microbes and forests now determine where people can walk, hunt, and remain alive. Eventually, the ice retreats and the sea returns. But the real turning point is not simply warmth. The violent swings narrow, seasons become more dependable, landscapes stop changing faster than human memory. The official beginning of the Holocene, our current geological epoch, is recorded in a Greenland ice core. Its chemical signal shifts over roughly 3 years. A planetary transition appears as a boundary thin enough to pass within one human lifetime. An ice core is a vertical archive. Snow traps dust and chemicals, then disappears beneath the next layer. Reading downward is like turning pages backward. What follows is not perfect calm, but compared with the ancient worlds behind us, climate remains inside a narrower range. Coastlines become familiar. Seasons become reliable enough for people to plant, harvest, and build in one place. That is the answer to the mystery of ancient Earth's deadliest eras. They are not simply ages with larger predators. They are moments when the planet changes the rules faster than life can respond. Oxygen becomes poison. Ice covers a world. Warmth shrinks bodies. A stable home becomes a trap without moving through space.